When you walk into a store and pick up a new smartphone, it feels flawless. The glass is immaculate, the edges are perfectly aligned, and the software boots up without a single stutter. It's easy to hold one of these devices and subconsciously assume it was simply born this way, as if it popped into existence fully formed and pristine. But the reality on the factory floor is much different. Every single piece of manufacturing machinery is in a constant, relentless tug-of-war against physical decay, friction, and entropy. The sleek glass slab sitting in your pocket is actually a hard-won victory. That perfection is an illusion, carefully maintained by a hidden army fighting off catastrophic equipment failure every hour of the day. This battle happens inside massive industrial hubs like Chennai, India. These mega-factories run constantly, churning out millions of units through dense mazes of automated robotics and assembly lines. Amidst the thousands of moving parts, you have highly skilled technicians acting as the glue between human logic and machine precision. They monitor banks of diagnostic screens, ensuring the automated jigs stay within strict parameters. Then, the inevitable happens. Deep inside the line, a B3I battery machine detects an anomaly. Gears lock up, error codes flash, and a production line that processes thousands of devices an hour suddenly screeches to a halt. A dead line is a logistical nightmare. Every minute the belt isn't moving, the factory bleeds thousands of dollars, supply chain schedules rupture, and quotas are missed entirely. With the belt frozen, the technician's role shifts. They now act as a crisis commander, holding the product's entire destiny in their hands as they race to identify the collapse. When the alarms sound on an Apple iPhone 14 project, the directly responsible individual, or DRI, steps into the chaos. Instead of guessing, they execute highly specific, predefined test plans. The first step is electrical stress testing, the HiPod test. Forcing a massive voltage surge through the circuitry checks the insulation. This data acts like a map, systematically eliminating healthy components to isolate the exact failing node. The situation complicates as the rear camera module, the RCAM, begins reporting mass anomalies entirely independent of the battery fault. Simultaneous, seemingly unrelated failures can completely overwhelm standard debugging protocols. It creates a fog of war where fixing one issue might just mask another. To survive this, the engineer has to abandon basic checklist triage. They have to step back and find the invisible thread tying these random hardware faults together. This requires a deeply logical framework known in manufacturing as the why analysis. You look at the final symptom and you ask why it happened over and over again until you hit the physical origin. The symptom: A-datum and B-datum films are pasting onto units with critical alignment issues. Margins are off by millimeters. The engineer traces the films to the automated pasting machines, discovering an erratic microstutter in the placement mechanism. Why is the machine stuttering? They dig past the software and inspect the physical hardware, finally identifying a deteriorating sensor that is feeding delayed coordinates to the robotic arm. With the true culprit exposed, the engineer pulls the correct electrical spare from inventory, swaps the failing sensor, and meticulously recalibrates the machine's operating parameters. Victory here requires more than a simple part swap. The engineer must ruthlessly hunt down and eradicate the root cause to ensure the line stays moving. The moment the recalibration is complete, the tension on the floor breaks. The line springs back to life, and the chaotic halt is replaced by the smooth, rhythmic hum of synchronized machinery. But the DRI doesn't walk away yet. They log the daily breakdown, update the YY analysis reports, and ensure the mechanical spare reserves are replenished for the next shift. Every single unit that was caught in the halt is then subjected to rigorous functional and in-circuit testing. The goal is absolute containment, guaranteeing no compromised board makes it out of the factory. An engineer knows they've won when there is zero physical evidence a crisis ever took place. They clean up the mess so perfectly that the final product reveals nothing about the chaos of its creation. Weeks later, a customer unboxes that exact phone, peels off the perfectly aligned protective film, and powers it on. That user will never know about the RCAM anomalies, the high-voltage HiPod tests, or the engineer who spent hours analyzing a robotic stutter deep into the night. Meanwhile, the automation engineers are already back on the floor, running diagnostics, checking spares, and preparing to face whatever mechanical breakdown tomorrow brings. Our reliance on flawless technology rests on a fragile physical reality, one built through the relentless, unseen battles of the engineers guarding the line.